A quick recap of what you learned last lesson. Last lesson I introduced the idea of field theory. Field theory is completely invented. It works really well and it's really complicated. We're just doing the basics of it, but it's invented to explain how these three action at a distance forces work. How can gravity work without contact? How can electricity work, like static electricity, like when you rubbed like a comb on your hair and then the comb bent a stream of water? How come the comb could put a force on the water when it wasn't touching it? And magnetism, how come these weird rocks seem to pivot and one end of them point towards the North Pole? Um, Up until field theory, there was this idea that it was almost like magical. And scientists didn't like that. Things don't happen because of magical effects. We need a better scientific explanation. So the explanation for gravity is all about mass. Any object with mass is surrounded by an invisible gravitational field. If we have two objects with mass and they're close enough together that their fields overlap, then it's the overlap of the fields that creates the force and stores energy. Similarly, anything with charge is surrounded by an invisible electric field. There's two kinds of charge, so we get two directions with electric field. Electric fields always point towards a negative and away from a positive because we imagine how that charge would influence an imaginary positive charge. More on that a little bit later. If we have two charges close enough together and their electric fields overlap, then it's the interaction of those two electric fields that's what creates the electric force and stores the electric energy. The last one, even more complicated, is magnetism. We're going to go with this kind of outdated but simple model that an object is magnetic if it's got its dipoles that it has in the object are lined up. So if dipoles in a material are lined up, then that material is a magnet, and the magnet is surrounded by an invisible magnetic field. So it's a little bit more complicated to why we have a magnet. Mass makes gravity. Charge makes electricity. Dipoles being lined up, that's what makes a magnet. The magnet is surrounded by an invisible magnetic field, and if we've got two of those close enough together that the fields overlap, then the overlap of those fields creates a magnetic force and stores magnetic potential energy. Magnets are a little bit weirder. You can't have a north without a south. You can have materials that become magnetic when they're around other magnets. You can have materials that are permanently always magnetic. You can have materials that are always not magnets, like wood and plastic. So magnetism is kind of the weird one, but it does fit the sort of symmetry there, that if you have two of them, the overlap of the fields creates the force and stores the energy. We're not going to talk about the energy in grade 11. We'll circle back to that in grade 12 physics. Okay, another thing we need to go over before electromagnetism will make sense. Way, way back, when they were coming up with electricity, they didn't have the whole picture figured out. So way, way, way back, when they were coming up with field theory, working on this electricity stuff, the physicists, the scientists that were working on field theory, they weren't chemists, so they didn't really understand the atom. And even if they did, the model of the atom wasn't done. So these electricity field theory kind of people, while they were building the model of field theory, of electricity and current and things that all ties together, they didn't know. They didn't know that it was electrons that were free to move around and positives were locked in the nucleus. At this point, no one knew that. So since they didn't know, as they drew circuits and things like that, they always imagined that it was the positives that moved around. So they knew there were two kinds of charge, one flavor and another flavor. It made sense to call them opposing words, so they chose positive and negative. That was a clever decision because it helped with the math. But they didn't know is that it was the negative little electrons that got pushed around. So when they were coming up with field theory, it's stuff that we've seen before. Part of field theory is electricity, part of electricity is circuits. So when they were working on circuits, this is our notation for drawing a battery. These parallel lines with one a little bit longer than the other one. The longer line is a positive terminal and the shorter line is a negative terminal. When these original scientists were talking about current, they always imagined that it was a positive that was moving. If we imagine it that way, if positives could move, they'd be repelled away from the positive terminal and attracted to the negative terminal of the battery. So if we drew a simple circle like this, just a reminder that these little squiggly lines, these little squiggly lines, that's the symbol for a resistor or a load. We could pretend that they're light bulbs. Over here, I've got our battery, long terminal, I'm going to exaggerate it, short terminal. The long terminal is always positive, the little terminal is negative. If it were positives that moved, they would get repelled away from the positive terminal. So they'd leave the big side of the battery and they'd kind of loop around the circuit going this way. Through the first resistor, onto the second resistor, through it, around the corner, through the third resistor, and get drawn back into the negative terminal of the battery. If we imagine a world where positives moved, we call it conventional current. And the conventional current, in this particular one with the battery that way, the positive current would go clockwise, be pushed out of the big terminal, loop around, and back into the battery at the negative terminal. If we pretend that all those resistors, those loads that I show that are there are light bulbs, then all those light bulbs would light up. If we're a grade 9 science, we'd maybe spend some time talking about circuits and how it's an equal current in all of them. We don't need that for now. We're not going to spend any time talking about circuit theory. All that I need you to get so far is if we're talking about conventional current is always out of the positive terminal and into the negative terminal. That's conventional current. Now, later, as this science was being developed, this guy, you don't have to memorize names, but sometimes in grade 9 chemistry you hear it, this guy named J.J. Thompson. He discovered the electron. The experiment that he did, we'll talk about it later, the experiment that he did actually used electricity and magnetism to figure it out. But he figured out that of these two flavors of charged particles, positive and negative, he still used those words, but he did an experiment to discover the electron and figured out that the electron is this teeny tiny light thing that's free to move around. As the model of the atom got better, they figured out that the positives are these big fat protons and they're locked in the nucleus. There's no way positives are going to move around a circuit because they're too big and fat and they're locked into the nucleus. Strong nuclear force with all these other protons. What we now know is that it's these wee little teeny tiny electrons that move around a circuit. So it breaks away from the convention that the field theory people thought about. So sometimes we call it negative flow current. But if we consider the exact same current, the exact same circuit, sorry, if I draw the battery, I'm going to exaggerate the long side, little side. Long side still positive, the little side still negative. Under negative flow interpretation, the little electrons are going to be repelled out of the negative terminal, which is the shorter line, and attracted into the positive terminal, which is the longer line. So according to electron flow, electrons would leave the little side of the battery, loop around this corner, go through this load first, pump through here, then they keep going around the corner, go through the next resistor, around the last corner, through that resistor, around the last corner, back to the battery. If these things were light bulbs, the light bulbs would all light up. The bottom line is, if we do it according to negative flow, the current would flow in the opposite direction. In negative flow, you can see that the current is flowing the way I've drawn the battery in this circuit, counterclockwise. The exact same circuit in this discussion, conventional or positive flow would go clockwise. But otherwise, it's the exact same outcome. If we built this circuit with 3 light bulbs, we get the same answer. The light bulbs would all light up. Just fundamentally, we're saying they're lit up for a different reason. Conventional theory, which isn't actually right, says that positives move clockwise through this particular circuit and lights up the light bulb. The more theoretically correct interpretation is that negatives moved counterclockwise, and that's why the light bulbs lit up. Because this field theory was made by some pretty important people, and they've made up some pretty cool science, even though they're wrong, conventional theory, the conventional current, still kind of hangs around. There are still people out there that will draw a circuit and show positives moving around the circuit, even though we know that's not how nature works. There are some people that drives them crazy, so they'll always show negative flow current because that's what actually is happening in the circuit. Electrons are being pushed around. Unfortunately, or fortunately, however you want to see it, I expect you to be good at both. If I give you, we're not going to do like circuits and Ohm's law, but if I give you a battery, you should be able to look at it and do both. You should be able to look at it and understand which direction conventional flow would go and understand which direction negative flow will go. So there's two kinds of current. Conventional current, which is kind of wrong, which assumes that it's positives being pushed around. Positives always get pushed out of the big terminal of the battery and into the little terminal. And there's also negative flow, which is technically more accurate because we know it's electrons that are light and move around, and they would move out of the little terminal and get pulled into the big terminal. But bottom line is we get the same effects whether we think of positive or negative. All right, I'm going to pause this video. I want you to watch this. Now we're setting up today's topic. That was all just sort of backgrounders. There's a huge, deep connection between electricity and magnetism. As I said earlier, you can't have one without the other. For today, we're going to call it electromagnetism. In grade 12, we're going to come back and talk about electromagnetic induction. I'm going to pause this particular video. What I would like you to do is watch this classic demo. It is, I can't remember how I word it in my video, but it is potentially one of the most important experiments that has a humongous impact, the most important impact on the development of society, on the development of how our quality of life is in the 21st century. So I'd like you to watch that video, and then I'll fire it up and I'll talk you through why you're seeing, or why you saw what you saw, and why it's so important.